What's up, everybody? It's Dan from SageMathTutoring.com, and here we are with another review sheet. This is for my calculus student who is in university, and there is a final coming up, and this is the review sheet for the final. So it's actually a really big review sheet, so I'm only going to do 6 problems at a time, and I'm going to kind of cut it up into different videos, actually. But I say we get started. Let's start with number 1. So we've got find the critical numbers of the function f of x equals x times 4 minus x cubed. So anytime they ask you for the critical numbers, what they're really saying is take the derivative and then set it equal to 0 and then solve for x. That's what they mean. So when we do that with problem number 1 with that function, we are going to have the following situation. Now, it is the case that we could multiply 4 minus x times itself, 3 times. We could cube that, but we could also use the product rule. I'm actually going to do the product rule instead. Now, the product rule acknowledges that there's a function here called x, and there's another function here called 4 minus x cubed. Now, I'm going to call x, that first function, g of x, and I'm going to call 4 minus x cubed, h of x, and that will be this. And what I'm going to do is I'm going to find the derivative of each of these separately. So that's going to be 1, and h prime of x is going to be 3 times 4 minus x squared, and that's going to be multiplied to the derivative of what's inside the parentheses, which would be negative 1 in that case. So if we were to rewrite that, it would be negative 3 times 4 minus x squared. So at that point, we could then begin the process of finding the derivative of the original function. And since we're using the product rule, that would be parentheses like this. And we would put the original thing here. We could say x right there. And then we're going to take the derivative of the next one. We already found the derivative of the next function, h of x. It's this, so it's going to be negative 3 times 4 minus x squared. And then we're going to take the derivative of the first one, which we already found here. It's 1 times the original h of x, which is 4 minus x cubed. 4 minus x cubed. And simplifying that, we would get, let's see, negative 3x times 4 minus x squared plus 4 minus x cubed. There's a GCF of 4 minus x squared, actually. Okay, so I'm going to factor that out. It's going to be 4 minus x squared, and that's going to be times negative 3x plus yet another 4 minus x. In case that's not clear, it's because we divided 4 minus x cubed by 4 minus x squared, which left us with 4 minus x. Now that, of course, could be simplified further. So that's going to turn into 4 minus x squared. I'll rewrite that part. And it's going to be the negative 3x combines with that negative x, and that's going to become negative 4x plus 4. And that is such that we want to set it equal to 0. Now, I think everyone would agree that if the first parentheses was equal to 0, then it would be 0 times that whole thing, and then it would be 0. And same with this. If that whole thing was a 0, then it would be 0 times this whole thing, and then it would be 0. So what we could do is we could set 4 minus x squared equal to 0. In doing so, you would quickly realize that x equals 4 in that case. And if we were to set this equal to 0, you would quickly realize that x equals 1. So that is the answer to that one. Those are the critical numbers. Okay, so now looking at problem number 2. Find the critical numbers of the function f of x equals x cubed, etc., etc. So that one I think is going to be a little bit more straightforward because I think we could just take the derivative of that using only the power rule, which should make our lives a little bit easier. So we're going to have f prime of x, that would be 3x squared plus 6x minus 24. If we were to set that equal to 0, that would be this, of course. And it's looking like we could divide everything by 3, and therefore we're looking at x squared plus 2x minus 8, and factoring that would give us, let's see, x. 4 and 2, definitely, and it would be plus 4 minus 2, so therefore x equals -4 and positive 2. Okay, so that is that one. All right, looking at problem number 3, find the absolute maximum and minimum values of this stuff. Okay, so first of all, finding the maximum and minimum values. This is going to feature a sine graph, but first and foremost, you do have to take the derivative. So we're going to start there. So the original function is f of x equals x minus 2 times cosine x, and we're looking at negative pi all the way to positive pi. Now, with regards to that derivative, it would be f prime of x equals 1. Now, the derivative of cosine is negative sine of x. So it's going to be negative 2 times negative sine of x, which is going to turn out to be plus 2 sine of x. And setting that equal to 0, which is something we're going to have to do to find the absolute maximum and minimum. So that would be 1 plus 2 sine of x. And at that point, we'd be subtracting 1 from both sides and then dividing by 2. So hopefully you understand it would become this. Now, the interval that we're taking interest in is negative pi all the way to pi. So negative pi is here, and then we're going to go all the way around to pi like that. So the question is, where in that interval is, for what angle, for what x value, is sine of x equal to -1/2? Well, sine corresponds with the y coordinate, so hopefully it's clear to most people watching that here's a y coordinate of -1/2, here's a y coordinate of -1/2. So to me, we're looking at these two angles. However, since the interval is negative pi to pi, we're going to say that this one is -5 pi over 6, and we're going to say that this one is negative pi over 6. So I'm showing that x equals -5 pi over 6 and negative pi over 6. Now the thing is, we're looking for the absolute max and min on this interval. So I think at this stage it would be a good idea to begin the process of drawing a sine chart where the final, or the leftmost point, would be negative pi and the rightmost point would be positive pi. Let's have 0 just in there as sort of a signpost or a milestone. And over here we have negative pi over 6. Well, that would be over here. So that's negative pi over 6. And then we would have -5 pi over 6, which would be over here. And at that point, we've really got 4 points that we need to take a look at. We have this point here, this point here, this point here, and this point here. And remember, this 0 is just kind of a placeholder, just a way of, helping me draw a nice looking graph, essentially. So that's perfectly in the center. But it's really these 4 points that we need to pay attention to, because these are the critical numbers, but at the same time, the end caps of this interval are also important. So what we want to do is we want to plug these four x values into the original function and see what the y value turns out to be, and also get a sense of which of those y values is the greatest, because in that case it's going to be the absolute maximum, and which of those y values is the least, in which case it's going to be the absolute minimum. So let's start with negative pi. Now, negative pi is over here. So what's nice about having the unit circle at your disposal is that you can sort of use it to figure out at least the cosine aspect of this situation. So when we plug in negative pi for x, I think we would agree, first of all, it would be f of negative pi, and that's going to equal negative pi minus 2 times cosine of negative pi. And cosine of negative pi would be -1. So ultimately, that would become negative pi minus 2 times -1, and that equals negative pi plus 2. So that is that x value. When we investigate the next x value, which is negative 5 pi over 6, that would end up becoming the following. So we'd have f of negative 5 pi over 6, and that's going to become negative 5 pi over 6 minus 2 times cosine of negative 5 pi over 6. Now, cosine of negative 5 pi over 6, when we look here, that would be all the way in this direction, and that would become negative radical 3 over 2 right there. So that would become negative 5 pi over 6 minus 2 times negative radical 3 over 2. And that would become negative 5 pi over 6 plus radical 3. So that is that one. So to sort of keep track of these function values, I'm just going to draw this blue box there. Okay, investigating the next one, which is negative pi over 6. That would be f of negative pi over 6, and that equals negative pi over 6 minus 2 times cosine of negative pi over 6. So cosine of negative pi over 6 would be right here. So that would be, if you can see this, that would end up being right here, and that would be radical 3 over 2. So ultimately this will become negative pi over 6 minus 2 times radical 3 over 2. The 2's would cancel, and we would have negative pi over 6 minus radical 3. So that's that one. And then finally, we would have to check out and see what happens with pi, which is the end cap over here. Now, when it comes to the unit circle, pi would be from here all the way there, and the cosine of that is -1. So we could sort of piece this together now. Let's see, I'll use yellow. So we have f of pi this time, and that's going to become pi minus 2 times cosine of pi. Now we already said that cosine of pi is -1, so that's going to become pi minus 2 times -1, and that is equal to pi plus 2. So that's that one. Now, when it comes to which one, let's start with the greatest. We can see how this is clearly the greatest. This is a negative number minus something. This is a negative number plus radical 3. Now, radical 3 is like 1 point something, whereas this is a positive number plus 2, and 2 is greater than this. So there's a positive number plus a number that's greater. So already this is the candidate so far for the absolute maximum. And this is the same thing as that, only it's minus pi, so this is clearly less than that one. So as far as the maximum, we're definitely looking at this value ultimately, okay? Because when they ask for the maximum, they're like, what's the y value? What's the highest y coordinate in this particular interval? Well, here it is. With regards to the least y coordinate in the interval, well, you'd have to kind of work it out. You would quickly see, though, that it's going to be this one. It's going to become negative pi over 6 minus radical 3. Negative pi over 6 minus radical 3. That is going to be, actually, that is the least value of all of these. Okay, so that's how you do that one. Okay, looking at the next one, which is problem number 4. Find the absolute maximum and minimum values of x times radical 4 minus x squared in the interval -1 to 2. So with regards to that one, let's do the power rule. Now I'm going to call the x g of x. So g of x equals x. We're going to call h of x radical 4 minus x squared, but I'm going to represent that as 4 minus x squared with a 1/2 over it. Now I'm going to now do the derivative of each of these. G prime of x is equal to 1. H prime of x is equal to 1/2 times 4 minus x squared to the -1/2. And that ends up becoming a chain rule situation, so I'd also have to multiply that by -2x. Now, simplifying that a little bit further, let's see, first of all, the 2's can cancel, and what I would have is a -x up top all over radical 4 minus x squared, okay? So that's what this would become. So keeping that in mind and proceeding with the derivative of f of x. So the derivative of f of x is going to be f prime of x, which is going to be a product rule scenario. That's what I'm going to do with it. And what belongs here? Well, it would be the first thing, which is just an x, okay? G of x, in other words. I called it g of x right there. It's just an x. And then it's going to be the derivative of the second thing. So that's -x over radical 4 minus x squared. And in this one, it's going to be the derivative of x, which is just 1, times the original situation here, which was radical 4 minus x squared. Radical 4 minus x squared. And simplifying a bit further, we would have -x squared over 4 minus x squared plus 4 minus x squared. Now we're still in the phase where we're trying to find the critical numbers, critical values. So we're going to set it equal to 0. We could add x squared over radical 4 minus x squared to both sides. We're going to have x squared over this minus x squared, and that's going to equal this 4 minus x squared. So at that point, I would certainly multiply both sides by the radical 4 minus x squared. And these would cancel, leaving us with x squared equals. Now, hopefully my student at home recognizes that this would just, the square roots would cancel, and it would just become 4 minus x squared. We could add x squared to both sides, giving us 2x squared equals 4. We could divide both sides by 2, which would give us x squared equals 2. And then quickly we would see that x equals plus minus radical 2. Now we are only concerned with the interval from -1 to 2, however, okay? We're only concerned with that interval. The interval from, let's see, -1 to 2, and negative radical 2 is outside of that interval, because negative radical 2 is negative 1 point something. So that's outside of the interval. So we only want to pay attention when we're doing the sine graph thing. We only want to pay attention to the positive radical 2, okay? But also, just like I said in the last problem, we want to pay attention to the end caps. Now, the end caps are negative 1/2 and also positive 2. And now we have discovered that one of the critical values we need to take into account is positive radical 2, which would be found, I'm not going to draw a 0 this time, that would be found somewhere around here, okay? I don't want to confuse the issue by drawing another number. So these are the values that you are going to want to take into account. You're going to want to plug them into the original function, which I'm going to rewrite soon, and find out which produces the greatest value and which produces the least value. So when I take into account the function, which I'm going to rewrite right now, it's going to be x times radical 4 minus x squared. And yeah, so maybe we could do this even in our head. So negative 1 is going to be negative 1 times, okay, now negative 1 squared is just positive 1. So it's going to become 4 minus 1 in there. 4 minus 1 is 3. So that's going to become negative 1 times radical 3. Negative 1 times radical 3. So that's going to give you this. When we plug in that for x, well, it's going to be a radical 2, first of all, times, now radical 2 squared is just 2, right? So it's going to become 4 minus 2, which is just 2. So it would become a radical 2 times a radical 2, which is just a 2. When I plug in 2 for x, it's going to become 2 times, well, let's see, it would be 4 minus 2 squared. Now, 2 squared is 4, so it would be 4 minus 4, which is 0. So it would be 0 times 2, which is 0. So certainly the least value is that, and certainly the greatest value is this one, okay? So that's the maximum, and that's the minimum. So that is the answer. As far as the answer, though, this is the minimum. You could write down the minimum is negative radical 3, and the maximum is 2. Okay, find all the values of C in 1, 4 that satisfy the conclusion of the mean value theorem for the function f of x defined on 1 to 4. So my student at home presented a really good formula for that. If you want to do this, it would be, I believe this right here, minus f of a all over b minus a. And that is the case when the interval goes from a to b. So our A in this case is clearly going to be 1. Our B in this case is clearly going to be 4. So for students at home, I'm not going to get into why this, the sort of the meaning of the mean value theorem as it pertains to a problem like this. It does have to do with something that is very intuitive. You could always find a YouTube video about that. It's very intuitive theorem ultimately. I'm a little bit more concerned with how to just go ahead and do the problem. And I would say to rely on this structure is pretty smart. Okay, it's pretty smart to rely on this structure. Now, nothing is better than sort of memorizing the structure and also understanding the concept. So, and in fact, understanding the concept, that might be the best idea because you can kind of piece together this structure yourself once you understand the concept. But we're going to just dive right into this. Now, first of all, I'm going to focus only on the right-hand side. Certainly, it's going to be b minus a, so we already know that's going to become 4 minus 1. Now, what is f of b and what is f of a? Well, f of b is going to be f of 4. What is f of 4? F of 4 is what happens when you plug 4 in here. That's going to become 4 over 6, aka 2/3. So that's going to become 2/3 minus f of a. Well, what is f of a? F of a is f of 1. What is f of 1? F of 1 would be what happens when you plug 1 in for x. So that will become f of 1 equals 1 over 3. Now, what does that become? That becomes 1/3 up top over 3 down below, and that simplifies to 1/9. So that's the number we're going to set equal to f prime of c. Well, what is f prime of c? F prime of c is, first of all, the derivative of f of x. Now, f of x is this whole thing. It's x over x plus 2. Let's start by just finding the derivative of f of x. We're not going to worry about the c part just yet. Well, that's going to become a quotient rule situation where it's going to be something squared times all underneath something times something else minus brackets something times something else brackets. What belongs inside the parentheses on the bottom? Well, that would be the original denominator. Then we bring it immediately up here. Then we multiply that times the derivative of the numerator, which is 1. Then we have the derivative of the denominator, the original denominator, which is 1, times the original numerator, which is x. So then, simplifying further, that would become x plus 2 minus x all over x plus 2 squared, which I'm not really going to worry about, and that becomes 2 over x plus 2 squared. Now, what are we setting that whole thing equal to? Well, first of all, we need f prime of c. This is f prime of x. So let's figure out what f prime of c is. Well, that's easy. You just replace the x with a c. So if f prime of x is the blue thing that I just wrote, f prime of c would be the exact same thing, only with a c instead of the x. Very simple, right? So this needs to be set equal to this. And that's exactly what we're going to do. We're going to set that equal, set both of them equal to each other. And at that point, we really just have a proportion. We just have a proportion where we could cross multiply. That would become 18 equals c plus 2 squared. Taking the square root of both sides would be c plus 2 plus minus 3 radical 2. Now, let's see, the interval we're interested in is, let's see, from 1 to 4. So that's something to keep in mind soon. Let's subtract 2 from both sides. We would end up with -2 plus minus 3 radical 2. So that's what c equals. However, -2 minus 3 radical 2 is outside of the interval. So we're going to discard that one. And we're going to say that the only c value we're interested in is c equals -2 plus 3 radical 2. With problem number 6, in my opinion, the best approach is to graph it as we go. They want us to sketch a graph of the function that satisfies those conditions. Well, we're going to graph it as we go. Now, one thing I'm seeing is that what they do is they give you a bunch of numbers where there's apparently a lot of action, okay? Now, what I mean by that is you're going to want to take note of the number -2, 0, 1, 9, -2, 6, 9, and also 12. So I'm just going to sort of plot those points because those seem to be important points. So there's an important point at 0. There's an important point at -2. Uh, Apparently there's something going on with when x is 1. Apparently there's something going on when x is 9. Apparently over here there's something going on when x is 12, so we're going to kind of make sure that that's represented. And apparently there is something going on when x is 6 as well, okay? I actually think that when it comes to these kinds of problems, that's a decent approach right away to just kind of just take note of those points, okay? Or those x values, I should say. Now, let's see what they say. F of 0 equals 0. In other words, when x is 0, y is 0. So in other words, this point is on the graph. The graph passes through the origin, in other words. It's also the case that f prime of -2 equals f prime of 1 equals f prime of 9, and that all equals 0. So in other words, the slope of the curve at -2, 1, and 9 is 0, which means those are the moments where the graph or the curve changes direction. It's increasing, and then it starts decreasing. It's that pivot moment where it goes from increasing to decreasing or vice versa. That's what we would refer to as the f prime of x equaling 0. It's also the case that at the limit of f of x as x approaches infinity is equal to 0. So what that means is as x gets infinitely large to the right, there's a horizontal asymptote at 0. So I'm going to write this green dotted line representing a horizontal asymptote. It's also the case that the limit of f of x as x approaches 6 from both the left and the right, by the way, is negative infinity. So what that means is this shoots down as the function approaches the x value of 6 from both the left and the right. So I'm going to want to draw a vertical asymptote there. Okay, that's essentially what that means. There's a vertical asymptote there. All right, so that's good. And let's see. I'm going to say that this next section here, that pertains to the first derivative, which has to do with the slope being either positive or negative. That kind of tells you whether or not the graph is increasing or decreasing on a particular interval. And then over here, that is the second derivative. That tells you whether or not the graph is concave up or concave down on a particular interval. So we're going to kind of focus on two at a time. We'll keep it color coded. We're going to do a little sine chart underneath. Looks like we have negative infinity, -2, 1, 6, and 9 going on here. So I'm going to line those up with the graph above. Looks like there's something going on at 1. Looks like there is something definitely going on with 6. Looks like there's something going on with 9, not 12 so much, but 9. And what is going on? Well, apparently the slope is negative. In other words, the graph is decreasing from negative infinity to -2. So that means that this is happening. It's also the case that it's decreasing from 1 to 6 and from 9 to infinity. So it's decreasing here and here. Okay. They also mention that the graph is increasing from -2 to 1 and from 6 to 9. So from -2 to 1, it's increasing, and from 6 to 9, it's increasing. Now, what I'm going to do is sort of just make these partitions clear. I think that's going to be helpful in the future. I know this might seem kind of weird for my student at home, but I don't really know how to do this in a way that's not confusing. Okay. It's kind of difficult to explain this one in a way that's not at least a little bit confusing. So this kind of gives us a sense of, oh, what's happening to the graph here, what's happening to the graph here. Okay, now I'm going to draw another sine graph underneath, only this time in blue to keep it color coded. And it looks like here we're looking at 0, 6, 6, and 12. 0, 12. Yeah, 0, 6, and 12 are the MVPs here. So 0 would be right around there. 6 we already know is here, and 12 would be around there. And in that case, we are looking at a scenario where it's concave up. The second derivative is positive, which means it's concave up from negative infinity to 0 and from 12 to infinity. So it's concave up here, okay, and here. And it's also apparently, according to the bottom part, concave down in the other two intervals. Okay, so sticking with the general principle of connecting this stuff, we'll connect that. I'm going to extend the asymptote down here. Okay, so how can we piece all this information into some kind of a graph here? Well, let's see. It certainly looks like it's concave up and it's going down and then increasing. So I think it's safe to say that there's something like that happening here, right? We also know that it passes through the origin. Passes through the origin. But once it makes it to 1, according to this information, it changes direction. So it goes down, and then it shoots down forever, because there's that asymptote there. I feel confident in that. I'm going to start to draw this, okay? So let's see. So what did I even say? Well, it goes up forever like this, and then it goes through the origin, and right around here, it changes direction, and then it shoots down forever, right? So that's what it does. Now you might be wondering, well, how can it pass through the asymptote? I thought you're not allowed to pass through an asymptote. Well, actually, you are. The asymptote, for example, horizontal asymptote in particular, tells you the behavior of the graph in the long run. And really, with regards to this horizontal asymptote, that corresponds to this piece of information, whereas x gets increasingly large. In other words, as it goes this way, it's going to eventually approximate that horizontal asymptote. All right, so that's important. Now, we also have the situation where we know that it goes down forever here as well. All right, now how do I know that? Because from this information, the limit of f of x as x approaches 6 from the left and the right approaches negative infinity, which means that as x approaches 6 from the left, it goes down forever, and as it approaches 6 from the right, it goes down forever. So we're going to want that downward arrow there. Now, apparently, it changes direction around there, and then it goes down. And then it switches to concave up. So I can kind of see what's going to happen here. What happens is it goes up, it changes direction here. But once it gets to 12, that's when it switches to concave up, which means it rounds off like that. Okay. Now I'm going to make that a little bit more dramatic, I think, to sort of hammer the point home a little better, because I understand this could be confusing. I want to make that move right there a little bit more dramatic. Okay, we're going to make that a little bit more dramatic. So it goes all the way up. We're going to make it all the way up here. Then it goes down. And then around 12, it hits this inflection point where it goes from concave down to concave up. That's the inflection point where it's now going from concave down to concave up. But what it's doing is it approaches this horizontal asymptote as x gets infinitely larger. Now notice the inflection point. This piece of information says it's concave down, then it goes concave up, which means it was concave down between 6 and 12. Well, I think we've represented that. It's certainly concave down between 6 and 12. And then right there, at that special moment, which I'll highlight in purple, that's the inflection point corresponding with this inflection point, where now it's going concave up. Now, I understand that it's getting closer and closer to this asymptote forever, but it's still this sort of upward facing bowl shape. Like you could pour water into it and the water would stay there. Whereas if you tried to pour water into this, it would just drop down, right? Or roll. If you poured it from above, it would roll off. Whereas if you poured it from above, it would stay there. That's one way of thinking about it. All right, so that's concave up. I'm hoping that's correct. I am curious to see what the teacher would say, what the professor would say about that. If you have any disagreements with me about that one at home, please let me know. I'm comfortable having this go up forever. I don't see any reason why not. I mean, it is concave up between 0 and infinity. So we do want to preserve this kind of bowl shape situation, which means that for this to go up forever would be conducive to that. So I'm comfortable with that idea, even though there's this horizontal asymptote. Um, I definitely feel confident about this stuff here around the 6. And since it passed through the origin, that means that there has to be this moment where it went above the x-axis and then shot back down again. So anyway, once again, if you have any disagreements with me, please let me know in the comments, and we will take it from there. But anyway, for my student at home, this is the first of numerous videos based on the review sheet, so hopefully this was helpful.